Hello, I'm Hannah Donnert with the Collaborative on Health and the Environment. CHE enjoys bringing you the latest environmental health science through our partnership calls and webinars, science serves publications, and social media. I would like to welcome everyone to today's CHE partnership webinar, which is titled Innovative Methodological Approaches to Study Replacement Chemicals' Effects on Health, Flame Retardants and Bisphenol S. Our moderator today is Jerry Heindel, founder and director of Commonweal's Healthy Environment and Endocrine Disruptor Strategies. We will leave time following the presentation for a brief Q&A session. You may type in questions through the Q&A feature available on the menu bar at the top of your window at any point during the presentation. After the presentation, our moderator will read out questions for our panelists to respond to. We will get to as many comments and questions as we can during the Q&A period. For those of you who call in on the phone, we have posted slides to accompany today's webinar on our webpage. You can download these by going to healthandenvironment.org. Please scroll to the bottom of the page and select today's webinar. On the webinar page is a link to the slides. Everyone on this webinar is now muted with the exception of our moderator and our speakers. This webinar is scheduled to last for 45 minutes and is being recorded for our call and webinar archives. With that, I'll turn things over to you, Jerry.
Okay, thank you very much. Hi, everyone, and welcome to this week's exciting webinar. This actually is the first webinar jointly sponsored by CHE and HEEDS. And in case you're not aware, HEEDS stands for Healthy Environment and Endocrine Disruptor Strategies. It's the new website for the EDC field, and you can find it at heeds.org. So I'm very pleased to introduce today's speakers. Our first speaker is Dr. Karine Audouze. She is the Associate Professor in Systems Biology and Bioinformatics at the University of Paris. Her main research interests are in the development of computational systems biology and predictive toxicology models. And she does that in order to investigate the effects of exposure to environmental chemicals on human health. She's also the principal investigator of the European 2020 project Oberon, which will develop in vitro methods to test for chemicals which disrupt metabolism, leading to obesity, diabetes, and liver disease. Our second speaker is Dr. Lola Bajard. She is a scientist working at the Research Center for Toxic Compounds in the Environment at Masaryk University in Brno, Czech Republic. She is particularly interested in mechanistic-based toxicology and how these techniques can be used to prioritize and predict health effects of novel chemicals. She is a part, again, of a large European project, the Human Biomonitoring for Europe. As you're all aware, a major goal of research on endocrine disruptors is to understand their mechanism of action. Both speakers today will focus on their novel approaches to identify mechanisms of actions of environmental chemicals. And they're doing this by integrating data from a variety of sources that actually are readily available for information. What they're going to show is that this data that's available, if you know where to look for it and how to integrate it and put it together, can be very useful. So we will hear both speakers and then answer questions for both of them at the end. So I'll now turn the webinar over to Dr. Audouze.
So thank you very much, Jerry. So I'm going to talk about a new computational approach that combines artificial intelligence and systems biology for bisphenol S toxicity evaluation. This work is part of the European project HBM4U that deals with the study of human biomonitoring in Europe. Humans are exposed to various chemicals via different sources such as cosmetics, diets, medicines, and the environment. And exposure to these chemicals can produce various health effects, such as endocrine disruption or metabolic disruption, and to identify which chemicals can be harmful and how they can be harmful, several approaches can be used. For example, epidemiological studies or experimental studies, in vitro or in vivo, including as well high throughput studies like omics analysis. And all these methods generate a lot of toxicity data which are available, but they can be sparse. They can be found in several publications or in various databases. So there is a need to better explore all these data and to optimally interpret them. And this can be done by computational modeling. So the aim of developing computational methods to predictive toxicology is, for example, to facilitate the establishment of links between a chemical and a biological event. The final goal being to help further experiments and decision markers assessing chemicals toxicity. So the strategies that I will introduce today, as well as the next speaker, Lola Bajard, focus on developing new approaches to speed up the identification of linkage between a chemical and biological events, and more specifically, adverse outcome pathways. The concept of adverse outcome pathways, AOP, has been defined 9 years ago by Ankley and is part of what we can call the modern toxicology. AOP are designed to describe existing knowledges. So an AOP consists of several biological events at different levels of the biological organization. So for example, it can be at molecular level, cellular, tissue, organ, etc. And the aim is to connect biological perturbations leading to toxic events that are named adverse outcomes. Each AOP starts from an initial event between a stressor, and the stressor can be a chemical, but not only, it can be the variation of the temperature, or it can be a social stress. So a link between a stressor and a biological system. And this event is called molecular initiative events, MI. And then through a sequence of various key events, KI, connected by key events relationships, the perturbations may be linked to adverse outcome at either organism or population level. Actually, AOPs are expected to be used more and more in regulatory framework, since they aggregate mechanistic-based evidences in a biological plausible manner. Therefore, these AOPs appear to be very useful for chemical toxicity assessment. In the approach we have developed at INSERM in France is computer-based, and the aim was to provide some new hypotheses to develop AOP induced by a stressor such as the bisphenol S, BPS. The developed tools identify and extract available information by automatic screening of the literature related to a compound. So here it will be related to bisphenol S. And these results are combined with some data integration to generate some hypotheses to develop some adverse outcome pathways. To do so, we propose a multi-step procedure with 3 steps. The first one is the compilation and preparation of the data, then the extraction of relevant information, and the last step is the biological enrichment of the identified links. So more precisely, the first step consists of compiling existing information to develop 2 dictionaries, one dictionary for the chemicals, here the BPS, and one dictionary for the AOP. For the BPS, toxicity data have been generated and are available in different sources, such as publication or databases. And to interpret as much as possible this data, we need first to identify them and then to compile them. So to develop the BPS dictionary, we took into consideration all synonyms for this chemical. So actually, we identify 131 synonyms using the PubChem database. Then abstracts from the scientific literature related to BPS or to the synonyms were compiled, prepared, and stored in an in-house database. And for BPS, we identify 109 relevant abstracts. The second dictionary is the AOP dictionary. It consists of listing the different terms for Mi, Ki, and AO existing in the AOP wiki database. This information was also stored in the in-house database. As a second step, the newly developed tool AOP-helpFinder, which is based on text mining, was used to identify co-occurrence between the BPS, here the black circle, and AOP terms that could be Mi, Ki, and AO. And as a result, we could identify links between BPS and AOPs from the selected abstract. Then the last step, we performed an integrative system biology approach in order to enrich this connection BPS-AOPs. And here it's represented by the dashed lines. And we integrated information from the TOSCAST and the AOP databases. And as a last step, to increase this information between BPS and AOP, we also did a manual curation of the relevant scientific publications that were identified during the text mining process. The AOP-helpFinder tool, so how does it work? So this tool is a hybrid method that is based on text mining and graph theory. The text mining, which is an artificial intelligence method, will allow to identify and extract in an automatic way the AOP terms present in the selected scientific abstract. The graph theory will allow to establish some score to quantify the information identified by text mining in order to keep the most relevant one. So the first step of the tool is to prepare the selected abstract to allow the computer to analyze them. So this is done in several steps. The abstracts are split in sentences. Then for each sentence, we look at the words and remove the negative sentence. Then we remove the stop words that are common words that doesn't bring any scientific information and the words related to punctuation and coordination. And as a last step, we kept only the root of each word that we call the stem process. And at the end of this process, the abstracts are clean and easily workable by the computer. Then we can process to the text mining step, which will consist in identifying AOP term in the clean abstracts. So the text mining will automatically search for co-occurrence of terms that will be quantified using two different scores. And this score system is performed to keep only the most significant finding. So regarding the two scores we developed, we have a position score to identify adverse outcomes, which are usually more related to one or few words, like, for example, adipogenesis or liver steatosis. And this score will give information related to the position of the adverse outcome in the abstract. So generally, in scientific publications, introduction and working hypotheses can be found at the beginning of an abstract, as you can see here in yellow for obesity and bisphenol S, whereas result and conclusion are more likely to be at the end of the abstract, as you can see in green here. Therefore, the developed score will allow to differentiate a working hypothesis from the findings. The second score is a distance score. It has been developed to identify the Mi and the Ki in the abstract, knowing that both can be more related to complex sentences. For the Ki, the most simple one has 1 word, and the more complex one has 21 words in the version of AOP Wiki we used. Here the abstracts are considered as an acyclic graph, meaning that each word corresponds to 1 node in a graph. Then we will calculate at the distance between the words. As a result, in this example, we could highlight BPS and obesogenic effect. This combined strategy has been applied to BPS, and here you can see a visualization, a network visualization of the result of the text mining step. So from the 109 selected abstracts related to BPS, the AOP-helpFinder identified 31 abstracts represented in green on the network that mention at least 1 co-occurrence between BPS and 1 AOP term. And in total, we were able to retrieve 44 Mi-Ki that you can see in blue and 4 AO in red. So the main outcomes were linked to reproductive health, endocrine disruption, and impairments of metabolism, including obesity. And based on the calculated score, the link between BPS and obesity was very significant. And looking at the result, it turned out that obesity is mentioned in 6 of the 31 publications, as you can see on the network. Therefore, we decided to explore this linkage, as very few publications mention directly this connection. Then, to have a more accurate assessment of the connection BPS-obesity, we performed a biological enrichment by integrating information from different sources. We use the TOSCAST and the AOP Wiki databases. This allows us to propose a potential mode of action for BPS leading to obesity. The red arrows represent the finding from the text mining, the green arrow information from the TOSCAST, and the blue one from the AOP Wiki. And we went one step further in order to attempt to get a more comprehensive biological mechanism linking BPS to obesity. For this step, we read the full publications of the 6 identified abstracts by text mining, as well as some relevant citations in this publication. And this allows us to propose a potential mechanistic effect linking BPS to obesity that involves several molecular targets in green, molecular processes in purple, and hormone disruption in yellow. And the arrows indicate if the effect is activation or inhibition. To conclude, I have presented a new computational approach that integrates a new tool, AOP-helpFinder, with system biology. The novelty of this tool is that it consists of an hybrid approach that combining text mining and graph theory. And here we mine existing information from various sources to make new observations or to confirm suspected effects. So this advantage is a rapid automatic screening of available publications and the complementarity to existing predictive system toxicology models. Such approach may help to increase our knowledge and may give orientation for further experimental analysis, and can also support the development of models that provide alternatives to animal testing. As such approach helps to improve our capacity to link environmental substances to AOPs, and then it can be very useful for prioritization of suspected chemicals. More information can be found as a recent publication in Environmental Health Perspective, and the AOP-helpFinder tools version 1, which is developed under the informatic language Python is available on GitHub with one example and a README. And finally, I would like to thank people involved in this work and all of you for joining today. Thank you very much.
Thank you very much, Dr. Audouze. Your talk was great, and we're looking forward to hearing now from Dr. Bajard, who's going to set up her slides. And there she is. Dr. Bajard, take it away.
Hi, everyone. Thank you for invitation. Thank you also, Karine, for a very nice introduction on the key concepts that I will mention also during this presentation. And today I will show you how we use the mechanistic information, so AOPs, for instance, to help us evaluate the hazard and predict the effects on health of replacement flame retardants. So to start, and this project, this work that I will show today was done at Recetox, as already introduced by Jerry, and was part of a large European project, HBM4EU, Human Biometric for Europe. So I will start by introducing flame retardants. Okay, so yeah, these chemicals are added to materials, consumer products, textiles. Many of them we can find actually at home, as illustrated here. And they are added to these materials to delay flammability, as their name indicate, but they tend to leak from these materials, and they are broadly detected, particularly in dust and also in human mattresses. So people are exposed to flame retardants, and presumably chronically in indoor environments. And the situation now is the following. The long-used PBDEs and HBCDD, you have the full names on the slide, have been restricted during the years 2000, and since then, a bit more than a decade, hundreds of chemicals are used as a replacement, and they are quite diverse. And so we are now facing a challenge with evaluating all this large amount of diverse chemicals. So as part of the HBM4EU, we were provided a list of 62 flame retardants that were pre-selected by experts from the HBM4EU. And we focused our research on the replacement one, those that are not yet restricted. And this is 52 flame retardants. And our task was to evaluate their hazard and identify the mechanisms of toxicity. And so Karine already introduced what are these mechanisms of toxicity that actually leads from the effects of the at the level of the molecule to the impact on health. And I just want to give a few examples of how this can be really important and why do we care about those mechanisms of toxicity. And so, for example, it can be helpful to predict impact of chemicals on health based on knowledge at the level of the cell or the molecule. It can help provide mechanisms for health effects that have been described in only a few studies sometimes. It can also be useful to identify biomarkers of effects. So we had this list of 52 flame retardants, and the first thing we did was to collect toxicological data available, and we searched for open literature in PubMed, for example, and we also looked for reports from regulatory agencies that would mention toxicological studies, and we focused on in vivo studies, which means studies in animals and also human epidemiology studies. The conclusion from this is that there was not so many, so we also examined or explored the ToxCast tool that was also mentioned by Karine, and which contains in vitro information, so it's mostly test in cells. And so I will say a few words on this ToxCast, what that is. The ToxCast program was launched by US EPA, Environmental Protection Agency, as part of a global shift in toxicity testing toward alternatives to animal studies for reason of cost, time, and ethics. Also, the toxicity field tends to shift towards alternatives which are often tested in cell cultures, for example. And the ToxCast and Tox21 programs use high throughput methods to test thousands of chemicals over a very large spectrum of in vitro assays. And all these results are open access and easy access, I would say, through the ToxCast dashboard. And this is how this ToxCast dashboard looks like. You can select for your chemical, for example, and here I selected this flame retardants. And actually I found information for 28 of flame retardants from our initial list. And for this chemical, you can very easily have information on the number of assays in which it was tested. And you can also know very easily in how many assays the chemical was active. So from this information, we got quite quickly and easily the percentage of assays in which the flame retardant was active. And then you can select a given assay and get a bit more detailed information, such as, for example, the AC50, which gives you an idea of the amount of chemicals you need to see the effect. And the less amount of chemical you need to see the effect, the more the chemical is toxic. So the more this molecular target, PXR in this case, is likely to be a molecular target of the chemical. And so we also selected those lower AC50 as potential molecular targets. I don't have the time to go into the details of this, but the overall, by collecting this in vivo information and this in vitro information from ToxCast, still the information was scarce, which means only very few in vivo studies or information from ToxCast, or insufficient, which is basically no information, for the large majority of those flame retardants, which is 42 of them out of 52. And we found substantial information, which we fixed the threshold at least 10 in vivo studies for 10 flame retardants. And based on this information available, we evaluated the toxicological concern in vivo. And so for those 19 flame retardants, we just cannot evaluate it. For those 23 flame retardants, we considered that there would be a toxicological concern for 15, but this is based on scarce information, so this is not so solid. And for 10 of them, for the 10 flame retardants with substantial information, we conclude that 9 of them present a toxicological concern based on substantial information. And for the second part of this presentation, I will focus on these 9 flame retardants. So we have substantial information that indicates there is a toxicological concern, but still there's not so much. And in particular, the information is insufficient to clearly associate some health effects to exposure. Usually there are only very few studies. They are from different systems, and there is a real lack in human epidemiology studies also. And for those chemicals, there is no mechanism of toxicity that has been clearly identified. So the second tool we use to address those issues and try to make maximum use of the information that we found was the AOP wiki. So Karine already very nicely introduced the adverse outcome pathway, so I don't need to explain that again. And the AOP wiki is online knowledge base that is supported by several international authorities, and people, researchers can propose and develop AOPs, and all the information on existing AOPs, molecular initiating event, key events, adverse outcomes, are open access and also very easy to access through this AOP wiki. And in this wiki, each of those molecular initiating events, key events, adverse outcome pathways has its own page, and you can search for information. And so what we did, which is very similar to what Karine and her colleagues did, was to try and connect the information that we collected in the literature, research papers, reports, Toxcast. For those 9 flame retardants, here you can see their abbreviation. Didn't have place for full name. And we try to connect this information to the information from the AOP wiki, but we did it manually actually. And the question is how to merge those information. So this is how we proceeded. First, we identified individual biological effects from the complex information from the literature. So we kind of restructured it. Then we try to link those biological effects to existing key events from the AOP wiki. And then so this would link our chemical to one key event of an AOP, and then we try to select the AOPs that would constitute some plausible mechanisms for our chemical. And the criteria we applied there is that we selected AOPs for which we could link our chemicals to at least 3 key events. So I will now take you through these steps one by one in a bit more detail. The first step, identify individual biological effects. So we have a lot of information for all those chemicals. I said it's not so much, but it's still a lot to deal with, which is research papers. I just put a few examples. Research papers. This is an extract for a report from a regulatory agency, or data from Toxcast. And from this, we try to extract individual effects. So in this case, for example, that would be oxidative stress, decrease in sperm quality, liver cancer, PXR activation. And the second step was to take those individual biological effects and go to the AOP wiki to try and find the corresponding key event, if there is any. And this is how the AOP wiki looks like. And you can select for the page that interests you. And here I selected the page on the key events. And you can search for the key events that would correspond to some key terms. So in this case, the biological effect reported would be teratogenicity. So we found that, for example, one of our flame retardant is teratogenic. We put teratogenicity and we search. And the AOP wiki would link it to this key event, increased developmental defect. And so that would provide a link between one of our chemical and one key event, which in this case is the adverse outcome of one or more AOP, because sometimes the key events may belong to more AOPs. And so that provides one link. And then the step 3 was to select AOPs which we think are more likely to be mechanisms of toxicity for chemicals. And we selected AOPs for which we found linked to at least 3 key events. And another criteria was that this link would be strong for at least one of the key events. Strong means that we have enough information to support this and that the effect of the chemical is observed at relatively low doses. And this, so we selected AOPs for which we have linked at level of 3, any key event. So that could be these 3 levels, but that could also be another 3 levels and no connection to the adverse outcome, or that could be these 3, for example. So we didn't have a criteria there. It could be any. So in the next slide, I will show you the main, some of the main results we got from this search, and I will take little bit of time on this slide because there is a lot of information. The ovals represent the adverse outcomes, and the color code indicates that there were information linking the chemical with this adverse outcome. So, for example, we found information, some information, usually not so much, but some information showing that TDCI-PP, triphenyl phosphate, tricrysyl phosphate, and TCEP have effect on decreased semen quality. And overall, the main effects that we found from the literature were related to decrease in male fertility, or neurotoxicity, or hepatotoxicity. And the arrows represent the AOPs that we found as plausible AOPs for our chemicals, again with the color coding. And so in this example, for example, the number correspond to the number of the AOP. Each AOP is assigned a number, an ID. So the AOP 18 here was identified as a plausible mechanism for TDCI-PP, triphenyl phosphate, and TCEP, and it leads to a malformation of the male tract. So one of the main information in this figure here is that we found plausible mechanisms of toxicity that would underlie several health effects that had been reported for those chemicals, but usually with very few information. So that gives us much more confidence that those chemicals may indeed have this health effect. And the hexagons on the figures, they represent the molecular initiating event that correspond to those AOPs. And the fact that there is no color for most of those molecular initiating events indicates that either we don't have information, which is for most of them, that's the case, that we just don't know what the chemicals do to this molecular initiating event. In some cases, it could be that the literature indicates that they may not be targets, but basically, in most of the cases, we just don't have the information, and it means that this is a big gap to fully understand the mechanism of toxicity, and that it would need to be addressed in the future. So to conclude on the main findings that we had with this AOP search, we identified mechanisms that underlie the health effects for some of these health effects that were reported in only a few studies. That makes us more confident, and we also identified gaps in mechanistic knowledge, and for instance, lack of molecular targets. And also, this was not really illustrated in this picture, but we also find some cases where we have a plausible AOP, but no information on the adverse outcome, and so we would predict this as a potential health effect of the chemical. To conclude briefly, for those flame retardants with very little toxicological information, ToxCast was useful to some extent. We could predict toxicological concern for one chemical with no in vivo information, but it still has limitation. I didn't have time to go into that, but this is something that would need to be addressed in the future. And the AOP wiki was very useful to make optimum use of the data that we have and to identify the mechanisms and predict some health effects. It still has limitation though, and in particular, it's recent, so not all biological processes are represented in this wiki. And finally, I would like to thank HBM4EU for funding, my colleagues at Ristetox, Lisa Melimuk and Ludiek Blaha, who helped me with this work, and thank you for your attention.
Great, thank you so much, Dr. Bajard, for your presentation. Now it's time for our Q&A session. You may type in your questions to the Q&A feature available on the menu bar at the top of your window. We will get to as many comments and questions as we can. Jerry, would you like to read one of the questions out now?
Okay, great. Well, first of all, thank you very much for those presentations. So I'm really impressed how you put together different pieces of data to come up with such interesting mechanisms that are likely related to the health effects. And in both of your talks, I just was never really, I guess, up to speed on the AOP wiki and how useful that could really be. So I learned a lot today. So there's a question here. I'm not sure I understand how you address the word not in the AI. How do you know if an outcome is associated or not with exposure? That's for Karine.
Yeah. What I mean when I say that we remove the negative sentence is, for example, if you have sentences like BPA is not associated with bisphenol, with obesity. So BPA is not associated to obesity. That means that is stated in the abstract, there is no relationship. Then we won't take into consideration such kind of sentences.
So it says there's another question here, but I can't seem to pull it up. So if somebody asked a question, maybe you could try it again. It says 2 questions. But Hannah, maybe you can look.
I think it was just somebody saying that it was for Dr. Audouze, and then she,
Oh, okay, that's 2.
yeah.
All right.
Jerry, do you have any questions for our audience and for our speakers?
So I don't have particular questions. I'm just impressed with the overall how this has all worked together and how neatly the 2 of these talks came together. I'm going to have to think about it a little bit to come up with specific questions. That was a lot for me to get in.
There's a question that just came up now.
Can you show the results slide again? I want to see the 3 major findings. I don't know. So both of you maybe. The 3 major findings,
Yes.
the results slide.
So is it for me or?
Try that. Can you
So,
come back to the last slide?
yes. I don't know if I can come back actually. Yes. That was this one probably?
Yes.
Or
With the arrows, with the box that dropped it.
yeah, it's there's a lot of information there, but and actually the link here is the link to the paper. So all this is published, and you have the link here. And I think the presentation will be also available on your website after. So is there? I see that there are more questions.
So what's the website for the wiki? Can you tell us that? That seems to be the key thing here from both of your presentations. How to get to the wiki and how to is that a simple thing?
I think you have the link in one of your slides.
I had it at some point. I hope it didn't get removed. Maybe because now it's not there anymore. But I think Hannah, I think I put it in the references in the supporting information that you should have on the site, or
otherwise you can find it on our publication as well.
if
okay.
I'm sorry about that.
There's supporting publications on our website, and it's probably in there. If not, we can respond to that question.
I think I had given it in the supporting information.
So here's a question, and I guess it's for you, Lola. That pull up that slide with all the multicolored.
Yes. Yeah. Okay. So I will put it again.
That seems to be the key slide here. That was really nicely done.
Now I can't. Yes.
Okay. So the question is, if the MIE is missing, how do you choose the one indicated on the slide?
So this,
without colors, how do you?
yeah, yeah, that's a good point. I was not clear enough there. These are the molecular initiating event, the MIE, that correspond to the AOP. So an AOP, the arrow here, I said it represents the AOP, and it contains information on from MIE to adverse outcome. So what this says is that glucocorticoid receptor is the MIE for both those AOPs. So we identified this AOP as a plausible mechanism for TDC, IPP, triphenate phosphate, and tricresyl phosphate, but the link were at the other levels of the AOP. So we know that this is the molecular initiating event for this AOP, but we didn't find evidence that shows that those chemicals do affect this molecular initiating event. Not strong enough evidence, or no evidence. This is what it says. So either we need to test that again and test whether these chemicals do impact this molecular initiating event, or maybe we have to find another one that would lead to the similar chain of key events after. Yes, I hope that answers the question.
Okay, I think so. Okay, so that's all the questions for now.
Great. Well, I think then thank you so much to our speakers, Lola and Karine, and thank you, Jerry. We're approaching the end of our webinar today. A video recording of this webinar will be available on the CHE website soon. Tomorrow you will receive an email containing a link to the video. CHE's next call will take place next Tuesday, June 25th, and is titled Silicones and Food Contact Materials. Additionally, on June 27th, the CHE Alaska Partnership will host a call, Plastics and Health, the Hidden Costs of a Plastic Planet. To learn more and to RSVP, please visit our website at healthandenvironment.org. If you are new to CHE and would like to stay updated on upcoming events and more, please sign up to receive your our newsletter by selecting the Join Us tab at the top of any page on our website. Additionally, if you appreciate these CHE Partnership webinars, which bring you the latest environmental health research for free, we encourage you to support CHE's ongoing work by making a tax-deductible donation via our secure website. Thanks again, again, our website is healthandenvironment.org. With that, I would like to thank our speakers again, Dr. Audouze and Dr. Bajard, once more for taking the time to present today, and to you, Jerry, for your excellent moderation. Thank you for joining us, and have a great day.